Monique the speaker, right? You can hear me, right?
Yeah.
Okay, cool. Monique listen. I came direct from another class just now.
Welcome back to the channel, guys. Today we're here with Miss Ho. Yeah.
Yo.
Okay, yo, what's up?
Whoa.
Yeah, I think people are gonna unsubscribe. Right? They'll be like, who's this label wanna be? Okay, anyway, so shall I be the boring professor?
No.
Today we are going to be learning about how to conduct experiments. Alright, so I just want to show you the experiment to determine the specific heat capacity of materials. So what we have over here, obviously, you need to have the object which you're going to be investigating the value of. So this is the example of the aluminium block. So we haven't done this experiment yet for obvious reasons, because when we were learning this chapter, we were all at home. Okay, and this is a standard issue lab aluminium block. So wherever you go, whichever lab that you want to, I want to go and learn about aluminium specific capacity, this is the kind of block you always see. So it's always this cylinder shaped block. Okay, so this aluminium block, as you can see, there are two holes. Not for fun. Okay, let's try to recall specific heat capacity, right? How do we calculate specific heat capacity?
MC.
Okay.
C over MC. MC theta. Q over
MC.
MC.
There's a theta somewhere.
Why got so many
MC
figures
theta.
on there?
MC theta.
MC theta equals what?
Q.
Okay, so how do you count C?
C. Q over M.
Q over M theta. Yes, thank you. Q is what?
Heat.
Heat. Yes, heat. Okay, so when we want to be able to calculate or measure the amount of heat, right? The problem is we can't use general heaters like, let's use Bunsen burner. We can't, because how on earth are we going to be able to determine the value of heat which the Bunsen burner is emitting to the aluminium block? We can't, right? So that's why we had to find another way. In this case, we use an electrical heater. So this thing is an example of the electrical heater. Have you seen this before? Okay, now you see. Ideal heater that teacher talked about, and teacher tried to draw last time. This is the heater. I know it doesn't look like a heater. Trust me, it gets hot. So this heater is actually is used in the lab, and you can use this to heat up the aluminium block. Heat up water also can. So for example, this thing, this calorimeter, this is actually for water. If you want to measure specific heat capacity of water, right? So there's the insulation inside, okay, and then alright, okay. So this thing, the cover, you can see here there's a stirrer for you to stir the water stir, okay. And then you find, right, that the aluminium block, the hole is designed for this heater. Left foot, no? This one also. So this is, let's talk about aluminium first. So this hole is for the heater. So why we use an electrical heater? Because this heater, I know you later you can take a look. I know it's a very homemade label, but you can see the power rating on it later, right? You can come and take a closer look. Now I know your eyesight, like upper knee, cannot see anything. Then later you take a look. It's written here 50 watts. So why we use an electrical heater? Because this is based on the formula power equals energy over time. And energy equals power times time. Remember we learned this in class, right? So the assumption here we make is what? What's the assumption we make for heat? No heat loss to surrounding. That means all the heat released by the electrical heater will be absorbed by the aluminium block. Okay? So that's why when you calculate the energy released from the heater, we assume that to be the heat energy absorbed by the aluminium block. Okay, so instead of Q over M theta, we write it as PT over M theta. Power and time. Okay. M is what? Mass. Okay, so obviously the best practice is to get the weighing scale or a digital balance, and we measure the mass of the block. But because it's standard issue, wow, they write for you already 1,000 grams. You can see, right? See, they write down already. Wow, so no need to measure, no? Okay. So I know we're all lazy people, right? I'll just write like 1,000 grams. Theta is what? Change in temperature. How do we measure temperature?
Minus.
Thermometer. So with the thermometer, right? See the second hole is for what? See, wow, perfect fit, wow, for the thermometer. So itulah sebabnya ada dua lubang. Okay, that's the reason why we have two holes over there. Okay, so other things that we need. Okay, so anyway, so this thing is a tile, but we call it a mat. What is the purpose of this? What do you think?
To protect the table.
So it doesn't go like table.
Also, another way to express it, you can say it acts as an insulator, right? Okay, what other things do we need?
Electricity.
Okay, so the power supply unit, of course. Okay, the label for the power supply unit, you can take a look later. It does say 12 volts, so quite easy now when you connect about 12 volts. Alright? And what else we need? Forget this for a moment. What else we need?
Is that gasoline?
What's this thing?
Cotton.
So for those of you who want to dress up as Santa Claus later, I will do that. Okay? So what's this for?
Insulator.
Because we scared this fella gets cold at night, right? So we need to make it feel warm and happy. Okay, so this is an insulator, right? To prevent, not prevent, you can't say prevent. It's to what? Reduce heat loss. Why do you think we have this bottle here for?
Is that gas?
Fire.
Drink.
Get
Fire.
Oh, motorcycle I can use for my motorbike. Okay, so remember that, in fact, if you take a closer look, I think you can see some oil spilled out already. So we put the oil a little bit inside the two holes because the oil will help the heat to transfer better. Because oils are the good heat conductor, air is not. So if you don't have any oil inside, what happens is, although it's designed to fit but there is there's a little thin layer of air, so the air is not exactly the best heat conductor. So air actually acts as a little bit like an insulator. So putting a little bit of oil, when you put a little bit of oil doesn't mean you pour the whole thing inside. You just put a few drops of oil inside. That will coat the lining of the hole so that the heat from the heater goes to the oil to the aluminium block, thermometer, then it's from the aluminium block to the oil to the thermometer for better heat conduction. It's just to minimize any heat, the other heat loss. Okay. So, any questions? You want to take a closer look? What about trust? It's about whether you want to see this or not. Okay, and then this is the calorimeter. I think this morning, okay, so this, I just want to show you so at least you are aware now. When you're like, ooh, this is what the aluminium block looks like. So now it's not just based on diagram. No questions? Then I'll show you the light experiment. Now we go back that side. But for the light experiment, we need to do this in a dark room. You do this in a bright room, you can't really see stuff. But never mind, I show you first. Okay, let's look at the light experiment. So I brought you ahead of the total internal reflection topic. So we've learned up to topic 6.1, which is refraction. We haven't gone into 6.2 total internal reflection yet, but I'm bringing you guys into the lab ahead of the topic because you're not coming to school next week, right? You guys will be online, so you won't get to come to the lab. And then this whole week I barely saw you because yesterday I had invigilation, tomorrow is class party, so no physics, right? So I'm just going to show you the activities that are done to investigate the light phenomena. So we already know that light is a type of wave. You have learned about reflection, refraction, diffraction, and interference. Now, this morning I'm going to show you the refraction experiment for light only. If we have time, I might show you the ripple kind. Okay, so
Christmas.
the most boring Christmas present. Is it sealed? Why you give me a sealed one? Boom. Yesterday I just opened one box and now we give me another one. This one no need lah. This is fine. Okay, so this is a ray box. So when we say ray box, you should look at your textbook. There's a ray box. Okay, ray box. So the ray box basically there's a box with a light bulb inside. You switch on.
Oh, wow.
Can see, okay, it's a bit dim though. Yeah.
Report.
Wait, after me.
Roll line before worry.
Why is everything falling apart? So go back next. Okay. Anyway, so this ray box, as you can see, there are grooves inside. Let me off first. Okay, you can see the grooves inside, right? So normally these ray boxes, right, they come with this kind of I forgot what you call it. Well, this kind of screen, okay, which has one slit, three slits. So why? Because when we do light experiments, we don't want to use the entire boom, we want to use a single ray of light or 3 rays of light. So that's how you get a single ray of light. Okay. Later we'll switch off the light so you can see more clearly, because now you can't really see right? In fact, why don't we switch off the lights right now?
Yes! No, off.
For light experiments, you need to do this in a room that's dark, because otherwise we can't see the light rays clearly. So,
And now you're the spotlight.
no.
I want to be the No.
Okay, so you get the single ray of light. Okay. And 3 rays. We actually should use paper. So I'm just going to so that you can see it even more clearly lah. 3 ray. In fact, here is better because then you have less divergence. Okay, so can you all see Hey, you all see? Never mind lah. You make sure you all see ma.
Can the camera see?
The camera can see, but this camera cannot see. Like they will just see.
You'll just see Miss Who.
I think they cannot see the full area of light. Too bad lah. Next week you all can see in person lah. Anyway. Okay, so just to show you, right? Okay, if we were doing a refraction experiment with a glass block, okay, with a glass block, can you all see? Is it too dark for you to see?
No. It's fine. Just nice.
Just nice. Okay. So I know, right? So to study light refraction, obviously we can use a rectangular glass block. Now, we don't want to work with a ray box with such a like a big beam of light, because how will I want to study refraction? Nothing to study, right? That's why we use with a single ray of light. You can see, okay. So.
Did you just forget about
So let's say we were doing a refraction experiment. So what we would normally do is a glass block, we would trace the outlines with a pencil and we change the angle at which you shine the light ray at. So of course you can see the bigger the angle, right? Then you should be able to see that it's not a straight line. If you look it from the top, you can see it from the top. Yeah. Can you see the refraction a little bit? But if you look inside the glass block, you can't see the light ray traveling inside the glass block. Disappear. Yeah, because it's the glass block, the optical density is too great, so you can't see the light ray traveling in it. So anyone who asks you, oh, can you see the light ray inside the glass block? Now you see, you can tell lah, you can see lah, where can see one, okay? Unless you got superpower lah, I don't know, Superman, you can see the light ray, then okay lah. But the rest of us mortals cannot see, so just to show you, okay? So how we would normally do the experiment, and we're not going to do that today, so maybe next year if I'm teaching you. So what we normally do is trace the outlines, then where the light rays are, right, we actually have to mark, draw, connect the rays based on what we can see, take off the glass block, then we reconnect, and then we can measure the angle, because right now, to measure the angle, you can't, because you can't see the light rays. How to measure the angle, right? If you're going to try a larger angle, it's okay. Okay? Now, do you remember that? No, you haven't learned yet, so you can't remember anything. Okay, I just want to point out to you now every time light undergoes refraction, a small percentage of light is reflected. So look on this side. Can you see a small percent? See a little bit of light ray reflected here? Can you see it now? Little bit. Okay, so can you see here? A bit reflected? Can you see it now? I put here a bit. Can you see? Can you all see? Let's see lah. Can see okay. So, do you see a little bit of light is reflected, right? So this is relevant to topic 6.2. Total internal reflection. Now, total internal reflection, the name is so the panjang after ini ya. Okay. So for total internal reflection, total internal reflection is not reflection. It sounds like reflection, it behaves like reflection, it's not reflection. It's actually a subtopic under refraction. Refraction. So, I'll show you an example of total internal reflection. Can you see how the light has reflected like that?
Yes. Yeah. Oh, I see.
Cool. So instead of coming out the other side, it's gone and reflected somewhere else. Right? Okay. But using a rectangular glass block is not the best way to observe total internal reflection. So normally we'll observe it using a semicircle block. Okay, semicircle. Okay, why?
Oh.
Okay, wait, let me.
You don't see much before.
Oh, this is like
I'm such a klutz. You can do it again.
Just put it down.
Okay, so I'm drawing a line here. Because this is where I'm going to place a semicircular block. So there's a reason why we're using a semicircular block. But I'll show you in a moment. Okay? And I'm taking a mark here, which is where the center of the semicircle should be. Okay, ideally, this should be done also when you're doing this experiment, you should get a protractor so you can measure the angles and stuff. But I'm just going to show you without the specific angle measurement. Okay, one of the problems with using a rectangular block is that you can't control the angle at which the light ray exits the glass block. Right? Okay, because it's parallel sides, then we know this light ray and this light ray parallel. Not a straight line, but they are parallel. But no matter what happens, right, from here to here, there's refraction. The light ray will always refract towards or away from normal? Towards normal, higher optical density, right? So towards normal. When it comes out, away from normal. So there's always going to be an angle change. The angle's going to change from here to here to here. Now, when it comes to total internal reflection, we want to be able to find out what's the angle of exit. Not this exit inside here. But the thing is, it's very hard to control because this fellow's always going to change because of the way it is, right? So why we use this is because cannot breathe. Okay, so why we use a semicircle block is because what happens is at the edges of where the circle is, and you've learned circles before in maths, right? So if you connect a line from the center of the circle to the edge, and you measure the angle at the tangent, it's always
the same.
Right? Always 90 degrees. So what happens is, if I point the light ray towards that center marking, right, that I marked just now, and I really make sure I place it right at that center, right? Okay. So you'll find that, okay, I know this is very fascinating, but let's talk about this side first, okay? Can you see that let's see, I'll show you, okay? Can you see that the light ray is traveling a straight line from air into the semicircle? Can see it? So it's a straight line. So no matter how I point it, forget the outside here first, this part is always a straight line. From air into the plastic. This is plastic, by the way. It's not glass. Okay? It's always from air to plastic. So as long as I point the light ray towards that center, it's always a straight line from air to plastic. So why we want this is because that way we can control the angle at which the light ray is coming out from the semicircle. Because here it's like straight line, then we can measure the angle inside going outside. Okay? So you can see, right? If the angle measuring from from this normal line, if the angle is small, can you see how it's just okay lah? Let's go out, refractive like normal, right? Okay, and can you also see a small percentage of light is reflected back? Okay, can see Okay, the bigger the angle of exit is, the stronger the light reflected will be. Watch, Can you see how it's getting? Wait, happening? Why suddenly like? Okay, can you see that the light ray is getting stronger as it reflects back? So again, refraction, right? So as we turn, why is it not showing up? You see, it's actually getting brighter and it's getting dimmer. It's not obvious. Just now was very obvious. I don't know why suddenly it changed. Let's see, lah. It's not. It's a bit dark suddenly, right? I don't know. Put tired.
You know when they say people are burnt out?
It's a reference to the light bulb. It is a reference. Yeah. Okay. Yeah. Okay. Yeah. I think it's better. Okay. Can you see? Okay. Here. Okay lah. That's refraction. Very little light reflected. As we increase the angle, it's very subtle, but you can see this is getting brighter, right? And this is getting dimmer. It's not very obvious though. Then the closer I get, now it's getting brighter, right? The reflected light ray. Until one point, and you can see how this thing is bigger and bigger. Until one point, okay, no more already. Like here's very little, and now I do this, right? 100% reflected back. So this phenomenon is known as total internal reflection. Total means 100% light ray reflected. Total means 100%. Internal, it goes back inside. Because actually it's going inside the plastic, back inside the plastic, and it looks like reflection like that. So this phenomenon is quite unique. It's when the medium behaves like a mirror, even though there's no mirror. That's under topic 6.2. Okay, so one more time, I'll show you again. Normal refraction. Okay, with a little bit of reflection now, cannot see the light. Voila, a little bit there. Then we keep increasing the angle. Wow, it's getting bigger and bigger. Until, no more space already, right? Until like, wow, come up like all the way already along the boundary. Then 100% reflected back inside. This is total internal reflection. So we're going to learn a little bit more about this in theory in 6.2. Okay? Okay, anything you'd like to ask with regards to this? Okay. No? Then I'll show you one more thing. Not one lah, it's okay, that's one set. Okay, let's look at three ways. Okay, this one is the shape of a convex lens. You've learned before, right? Convex lens, how do the light rays behave?
X.
How focus to
This is the proof, okay? So obviously this time we use three rays lah. If you use one ray, like what are you looking at? I also don't know what you're looking at, okay? So that's why three rays. So that's why lah, single ray, triple ray, okay? Last about me, okay? So this is the convex lens. Then let's say this time you have the friend now who decided that need to lose weight. So you get the skinny fella. Okay? Skinny. Same shape, but it's skinnier, right? Then you see the difference? It converges, the light rays focus further away. So the fatter fella, okay, shorter points of focus, longer.
So what if you put both? Okay.
Okay. So this is not a convex lens, but this is the shape of a convex lens, and the purpose of this is because if we have the actual convex lens, actual convex lens. There is an experiment that you do need to learn to use actual convex lens, but I think we'll do that next year lah. Because
Try.
this one I cannot see. I tried many times yesterday. Can't really see. It's too dense. Yeah. If you use without, probably better.
Shadow.
Yeah. But it's too focused. Yeah. So with triple light rays, it's quite hard to use. But there's an experiment that we do need to do with the convex lens. We do. Okay. But that one you need to use. Okay. You need to put it there.
Why does light not pass through the glass?
It's
Yeah. No, it's not.
actually can, but it will focus much further away because this one has a focal length of 10 cm. So it will go a bit beyond.
Yeah. Rainbow. You can see rainbow.
Wow.
Yeah, it's a bit further. It's like because it's a little bit.
I'm gay.
Yeah.
Sorry.
Hey, you found your new friend. Amelia, Emma, and Nadia. Bye.
It looks actually rainbow.
Yeah, this one we see a clear rainbow convex.
No, I'm not. Oh, wow.
Concave.
Looks like flower.
Okay, what about this one?
Concave.
Yes, you can see it. You all can see it. Okay, so this is the anorexic person who tak cukup makan. Okay, this one, right? Then the light rays how?
Not focused at one point.
This. Out.
Inilah buktinya. Okay, so this is the proof. So again, this is just to show students how the light rays would behave lah when they pass through the lenses. So again, there's also an actual concave lens. This one easier to see somehow.
Why?
Because of the lack of focus. Yeah. Like this one, the focus is forward, so that's why it goes quite far. But this one, the focus is at the back.
So if
So
you
it's
put
not-
glasses, is it gonna look like that?
yeah, it will work also. You wanna try? Yeah, you can try. But the difference is that your glasses are not double concave. So it's not so obvious. It's double concave.
No difference.
No power.
Rather a little bit.
There's just someone left. I know that.
Yeah.
Who left?
Your eye, when it perfectly round.
Yeah, very little because your power is not very high, is it?
It's 500.
So when it's quite high.
500.
Yeah, I'm blind. That's why I cannot use contacts. It's just like,
Okay, but double concave or double concave means both sides concave. Both sides concave. You can take a look.
and when you put it,
You may put the convex. Oh here. Yeah, you can take a look. This is a double convex. This is a double concave. So you can take a look. Right? You can take a look. Double concave. Pass it around the class so you can see. Those of you who are wearing glasses, usually it's not double concave. It's one side concave.
like 200 is That's what it wraps around your eye.
Do you have any questions at home?
It's not like it wraps around your eye.
Chắc tàu sống nha.
It's not. It is.
What we do with this? I also don't know. Looking at the lens. Oh, inilah. This is a lens. Then we'll talk about it in class next time. Yeah, we saw the lens.
But where's the camera? Woo!
Mini biscuit.
Oh, this one?
Mini biscuit.
Wait.
Double biscuit.
So while you're looking at the concave and
Concave.
I was going to ask you, while you're looking at the concave and convex, can you also just observe when you look at near objects and you look at far objects, what's the difference?
I don't know.
That's why you use the lens to observe. I know the answer, I know you all don't know. So you take the lens and you see, ma. Like that. So you look at near objects, you look at far objects. What's the difference?
New object. Look at my fingers. And look at that.
There's a difference, right?
Short-sighted.
When it's closer, it looks bigger. When further away, smaller and
Upside down.
upside down, right?
Really? It's so good. I cannot see anything at all. Try. What if I use strip glasses? Oh, okay.
Further, better.
So for concave left, no difference, right? Concave, you look near, you look far,
further beyond.
wherever you are. Okay, it still kind of the same, but just that nearer is bigger one, that's all.
Upside down.
Upside down, right?
Yeah. Which is the same as
So the reason I want you to just take note is because you'll be learning about lenses in the last topic. No, last topic 6.4. You'll be learning about lenses and the different positions of the objects will look different when you look at the lens. Different.
It's a Snapchat filter.
Are you? Okay, but anyway, time's up. I think we can stop here for now. Any questions you'd like to ask?
No.
No. You want to take a picture and send to your class, is it? Who asked you to miss physics? Oh. Okay, enough for today. Your turn next week. Okay, that's all for today. Thanks for watching, yo. Don't forget to hit subscribe.